Hello, I'm Bill Melbourne, and today I'm talking about the SABRE South experiment at the Stawell Underground Physics Laboratory. SABRE, which stands for Sodium-iodide with Active Background REjection, is an independent replication of the DAMA LIBRA experiment. SABRE South will be located at the Stawell Underground Physics Laboratory. Some of the key features of SABRE South is its Southern Hemisphere location with a northern twin, its low background crystals active veto system, 1 keV energy threshold to achieve a 1 to 6 keV region of interest, and the ability to use the veto systems for particle identification, localization, and to study the directionality. The SABRE South group is made up of 46 members across 5 institutions, located across Australia. So now I'll quickly discuss the Stawell Underground Physics Laboratory. So SUPL is the Southern Hemisphere's first deep underground physics lab suitable for dark matter and other low background experiments. It's located in an active gold mine in Stawell, Victoria, it's located approximately 240 kilometres northwest of Melbourne. The lab is 1,024 metres below the surface with a flat overburden. And access is via a helical shaft from the surface, and this journey takes approximately 30 minutes. The main cavern is operated as a radon-suppressed cleanroom. The muon flux of SUPL has been measured, and it's broadly in line with Bulby and the Gran Sasso National Laboratory. On to an overview of the layout of the lab. We have the main experimental hall, which has a minimum height of 12 metres throughout the space. Within this, we have the SABRE South experiment and its associated fluid handling facilities, as well as high purity germanium counting facilities. We also have the entryway with cleaning facilities to maintain the cleanroom status of the lab, as well as rest areas for anyone working in the lab space. Finally, there's a loading area to manage supplies and large equipment that needs access to the lab. So the main cavern of SUPL was excavated in June. Since the excavation, all of the walls have been pinned with steel pins, sprayed with a low radioactivity shotcrete, and are now being coated with Teflex to suppress the dust and radon emanating from the walls. So all of the materials used in the construction of SUPL are being screened for radioactivity using sodium iodide counting. We're currently on track for construction to be finished in December 2021, which will then allow us for SABRE South construction and commissioning in early 2022. So immediately after the lab's constructed, we're going to make measurements of the background in SUPL. So this includes a detailed study of the muons, not only their energy spectrum, but the angular dependence. This will be done using the muon veto panels from SABRE operated in a telescope orientation. We'll also be using a gamma ray spectrometer, and to measure the neutron spectrum, we'll use a series of bonospheres with a helium-3 detector. Now for an overview of the motivation for the SABRE experiment. The annual modulation of the dark matter interaction rate is a unique model-independent signal for dark matter, which is caused by the relative motion of the Earth through the galactic halo. This signal has a few key signatures. The first is that it has a period of 1 year. It's expected to peak on or around the 2nd of June, and the modulating component is between 1 and 3% of the total dark matter interaction rate. The DAMA experiments, first DAMA NAI and then DAMA LIBRA, have a 20-year record of this modulating signal in the 2 to 6 keV energy range. This has a combined significance of 12.9 sigma, and as you can see in the plot above, which shows the modulating component as a function of energy, this modulation is most pronounced between 1 and 3 keV, which makes matching this energy range crucial for any replication attempt. Recent modulation results from the ANIAS collaboration with a 314 kilogram year exposure found no evidence of a DAMA LIBRA-like modulation with a significance of about 3 sigma. The cosine 100 experiment, with an exposure of nearly 100 kilogram years, have a result compatible with the DAMA LIBRA modulation. But both of these current results are inconclusive, which means that a Southern Hemisphere detector with a similar sensitivity to DAMA is important for the replication efforts. Now, to discuss the SABRE South detector, we'll begin with our sodium-iodide crystal array, which is made up of our crystal detectors. Each of these consists of a sodium-iodide crystal with two 3-inch photomultiplier tubes. These are directly immersed within our liquid scintillator VITO, which consists of 12,000 litres of linear alkyl benzene, with PPO and bis-MSB as fluorophores. This is instrumented using 18 Hamamatsu 8-inch PMTs. Within this liquid scintillator volume, we also have calibration sources, as you can see here, which are used to both calibrate the crystal detectors and the liquid scintillator VITO. To finish off our VITO system, on the top of the experiment, we have our muon VITO, which provides 9.6 square meters of coverage. Our passive shielding for the SABRE experiment consists of polyethylene sandwiched between two layers of steel, which is done to reduce both the neutron and gamma backgrounds. SABRE South also has a passive dampening system where the VITO vessel meets the lab floor. This is done because the Stawell gold mine is still an active gold mine and there's regular blasting which can cause damage to the detector if not properly damped. SABRE South will have an array of 7 sodium iodide detectors directly immersed in the liquid VITO. This is done so that there's minimal material between the crystal and the liquid scintillator. These detectors are also purged with high purity dry nitrogen gas to minimize contamination. These detectors consist of our 7 kilogram sodium iodide crystal, which is doped with thallium. We expect this to have a light yield of about 10 photoelectrons per keV. This is directly coupled to two 3-inch Hamamatsu PMTs. These have a low background and have the low background full metal body. And we have a quantum efficiency in excess of 30% at 420 nanometers. So we read these photomultipliers out at 500 megasamples per second with a KN-V1730 digitizer. They're operated with a threshold that's approximately 0.3 times the single photoelectron peak height. All of this is contained within our enclosure structure, which is made of oxygen-free copper. We have a 3mm wall thickness to further minimize the amount of material between the crystal and the VITO, and the internal pieces within it are made of Teflon. Finally, at the top, we have the feed-through plate, which handles both the gas and electrical feed-throughs. The SABRE collaboration has successfully grown very low background sodium iodide crystals that are doped with thallium. For SABRE North, we have NAI33, which was measured in detail. And for more details on that and the methods and the results, please see Ambra Mariani's talk. For SABRE South, we have a new test crystal. It's 5 kilograms and was grown by radiation monitoring devices in Boston using a Bridgman stock barger process developed with the SABRE collaboration. ICP-MS measurements of the potassium show that the tip has 5 ppb, whilst the bulk of the crystal is below 10 parts per billion. This crystal is currently being prepared for counting at the Gran Sasso National Laboratory. One piece of ongoing work is AMS measurements to determine the lead-210 content of the astro-grade sodium iodide powder, and this is being done at the Australian National University. Now to discuss the active VITO system of SABRE South. So the VITO system provides full 4-pi coverage of our sodium iodide array. The liquid VITO system consists of 12,000 litres of linear alkyl benzene scintillator doped with PPO and bis-MSB. This is read out by 18 Hamamatsu R5912 PMTs, and these have the oil-proof base, allowing them to be directly immersed within our liquid scintillator. These are read out at 500 megasamples per second, also with the KN-V1730 digitizers. The active VITO system is primarily designed to VITO internal decays of potassium-40 within our crystals. It does this because as the potassium-40 decays, producing the 3.2 keV Auger electron, it also emits a gamma ray. This gamma ray can deposit energy within our liquid scintillator, which in turn produces scintillation light, which can be detected by our photomultiplier tubes. The active veto system is designed to veto these potassium-40 decays with an efficiency in excess of 85%. It's also built to be sensitive to any energy deposition above 100 keV, which makes it very useful for identifying other both external and internal background processes. Because of this, we expect the veto system to reduce the background by an order of magnitude within our region of interest, which again is 1 to 6 keV, as you can see in this summary plot from the SABRE proof of principle. The muon veto system provides additional tagging for cosmic muons. This is required to make detailed measurements of the muon modulation at the Stawell Underground Physics Laboratory. The muon veto system of the SABRE South experiment is made up of 8 EJ200 scintillator panels, which are 3 meters long, 40 centimeters wide, and 5 centimeters thick. These are coupled to light guides and PMTs at opposite ends. These PMTs are read out at 3.2 gigasamples per second, which gives us a longitudinal position resolution of 5 centimeters for muons passing through the detector. This is done by determining the difference in arrival time of the scintillation light at either end of the panel, and you can see here the data we use to extract this information. The data acquisition system for SABRE South comes under our general online systems. So each subdetector, which is the crystal, liquid veto, and muon veto system, will have a separate grouping of digitizers, but all of these will have a shared clock, and they're all read out by a fiber optic to our data acquisition computers, as you can see in the diagram below. We have an external trigger board which manages the combined trigger logic for the experiment and will issue event triggers to each subdetector. We do basic event building on site in the SUPL lab space before the data is sent to Melbourne University for further processing. Conditions monitoring is a really important feature of annual modulation experiments. We need this to ensure our detector performance is stable in the long term. There's an extensive range of sensors measuring things such as temperature in the veto vessel and within the crystal detectors themselves, the high voltage supplies of the PMTs, as well as things like the humidity in our nitrogen lines, liquid level within the veto system. We are also required to measure the vibration, as this is an active gold mine and there's regular blasting throughout the workday. We'll also be taking in various measurements from SUPL itself, such as the radon levels within the lab. The projected sensitivity of the SABRE South experiment has been estimated by Zarowski and Barberio. With 50 kilograms of sodium iodide and a projected background rate of 0.36 counts per day per kilogram per keV, for a DAMA-like signal, SABRE South should have a 5 sigma discovery power within 2 years and a 5 sigma exclusion power within 5 years. This discovery power is significant, as you can see in the plot on the bottom. Even with its delayed start, SABRE South will be one of the most sensitive experiments to a DAMA-like signal within a short range of time. We will also have the greatest modulation sensitivity with a 3-year exposure. For more details on this, as well as the process used to make these calculations, please see Madeline Zarowski's poster, The Influence of Sodium Iodide Background and Mass on Testing the DAMA Modulation. SABRE South has also made measurements of the sodium quenching factor in sodium iodide crystals that are doped with thallium, using a spectrum fitting technique for 30 to 300 keV neutron recoils. This was done using the Heavy Ion Accelerator facility at the Australian National University to generate a pulsed neutron beam. The recoil spectrum were determined using Markov chain Monte Carlo, which was then fit to the data floating the quenching factor. The results of this measurement are broadly in line with the existing literature, but new measurements are underway using astro-grade offcuts from the SABRE South test crystal, as well as measurements of the iodine quenching factor using the same method. To achieve a 1 keV threshold within our sodium iodide detectors, we require proper characterization of our photomultipliers to ensure they meet some basic requirements, in terms of quantum efficiency, gain, and the dark rate. We've developed a characterization process for the absolute quantum efficiency and single photoelectron response and gain using a picosecond pulsed laser. We also have a process for measuring the dark rate as a function of voltage and temperature, as well as a range of timing characteristics. On the right, you can see a basic block diagram of our absolute quantum efficiency setup, as well as the results from our charge model for single photoelectrons. We're currently developing noise rejection tools as well as an electron recoil versus nuclear recoil classifier. To discuss the status of the SABRE South experiment, we expect the delivery of the remaining PMTs in October. The crystal insertion system glove box has been built by Palazzi in Italy, and it's passed its leak tests. We've finalised the design for our crystal enclosure, and you can see a mock-up constructed below to test the insertion and assembly procedures. Our Vito vessel has been constructed locally in Victoria using low radioactivity steel and non-thoriated welding equipment. We've procured 17,000 litres of the base linear alkyl benzene scintillator from Nanjing via Juno and IHAB, and the Juno liquid scintillator properties are sufficient for our purposes. So the LAB has now arrived in Melbourne and is awaiting detector construction. So to conclude, the SABRE South experiment will be commissioned in early 2022 in the Stawell Underground Physics Laboratory. It's expected to reach a 5 sigma discovery sensitivity to a DAMA-like signal within 2 years. Some upcoming publications from the SABRE South group include the Monte Carlo simulation of the SABRE South background, the photomultiplier characterization methods and initial results, as well as a technical design report on the detector. We'd also like to acknowledge that the Stawell Underground Physics Laboratory was funded by the State Government of Victoria and the Australian Federal Government.